So for the progressive wave, equation of a progressive or traveling wave. Now, we can consider a wave that is of this nature. Well, probably there are two waves. You have one traveling, and the other did not start from the origin. This is Y and this is X. If this does not start from the origin, it can start somewhere like this. It can start like this, and finally. So I can say that this is Y equals to cos theta. Let's see. I can say this is Y is equals to A cos theta. I can say this is Y equals to A sine theta. So the one that started from origin, I'll call it sine theta. And the one that did not start from origin, I'll call it cos theta. Now, from here, it's easy for me to say, okay, good, that since Y is equals to A sine theta, or any of them, let me use sine theta. But recall from simple analysis that angular velocity is theta over t. This is for a progressive wave, a traveling wave. Now, if that theta over t, that is, what it means is that theta is angular velocity t. So I can put something like this here to become Y is equals to A sine Wt, which is angular velocity t. Now, this is one statement. And it's possible for me to progress with these two. I can decide to say, okay, if that's the case, anytime a wave is moving, there is something we call the wave constant. There is this thing that happens between them that whenever there is, it's a phase difference that happens between the waves. So if these two waves are moving in this form, in a sinusoidal wave or in a sinusoidal movement, this is an example of a sinusoidal movement. Because the movement is like, it's in a sinusoidal way, just like an alternating current. Unlike a direct current, is straight. Why is sinusoidal? It's of this form. So that's why we call it a sinusoidal wave. So it's sinusoidal movement. So you will say that, okay, somebody, you can address the statement like we use scientific statements, like somebody tell you that, oh, that person has a sinusoidal attitude, meaning his ways are sinusoidal. His behavior is sinusoidal, meaning it's not direct, not straightforward. So, if I consider in a sinusoidal wave, any sinusoidal movement will always have something we call that phase difference. So, the phase difference can be minimal, it can be insignificant. So, because of that, we must put it into consideration. So, we say Y is A sine Wt minus phase difference. It is denoted as phi, phase difference as phi. So you must take a note of this, very important. That's the first thing. But this phi itself, but the phi, which is the phase difference, phi itself is 2 pi x over lambda. That's another thing entirely. So if this is 2 pi x over lambda, which is phase where the wave phase difference, but there's something we call wave constant or wave number. Let me use wave number. The word wave number is given as k is equals to 2 pi over lambda. This is another thing entirely, and it is called wave number. And this is phi, phase difference, which is 2 pi x over lambda. Now, if I want to relate these two statements together, it's easy for me to say that now. I can say that, okay, good. If that's the case, I can say that y is equals to a sine wt minus, maybe I have something like, should have a bracket there. I have something like minus 2 pi x over lambda. That's my statement. So, but because this 2 pi lambda itself is k, so I can say y is a sine angular velocity d minus kx. So this is a statement of its own. You must take note of this, it's very important. Please don't forget, this A stands for amplitude. Stands for amplitude. So we'll take it again. A is A sine WT. So because we are now having a phase difference, that's why the bracket came in. So we have the phase difference as a phi, as a phi. So but the phi is 2 pi x over lambda. But wave number is given as k, which is 2 pi over lambda. So this analysis is A is angular velocity t minus 2 pi x over lambda. Now you have k to be this and this. Now this is simple. Now you have something of this nature. Please, the ones that I bracket are very, very key and very important. So you can have this, you can have this, still the same thing. But I want to add to this now. How do I add to that? It's easy to say that this value here, angular velocity itself, is equals to 2 pi f. That's the value. Angular velocity is equals to 2 pi f. So if this 2 pi f, I decide to make that value exist here as 2 pi f. So what will I call it? I will just move down there and say y is equals to a sine 2 pi f t minus 2 pi x over lambda. So now I have something of this nature. So from here, it's possible for me to now tell myself that, okay, good, this value here is a is equals to sine 2 pi, bringing it out, I will have ft minus x over lambda. But don't forget one thing. But we must remember that you must take note of the fact that the value v is equals to f lambda, and also that v is equals to lambda over t. Don't forget these two values. So because of these two values do exist, it is possible for us to say, okay, good, since these two values are possible, let's change the whole setting of this whole write-up. It's easy for us to do that. So I can, this f lambda and this v is lambda over t. So any of these values can change the whole writing of this system. Like, for example, I can say that lambda is vt. If I want to, I can say that v is f lambda if I want to. So from here, I can change f here to become v over lambda is equals to f. So if I put it here, it becomes y is equals to a sine 2 pi into bracket. What I'm having now is vt over lambda. Vt over lambda minus x over lambda. So I can have this. So any value you want to replace it with, you can replace it as far as these two equations are correct. So from here you can obtain any value you want to obtain. This is the main equation. Or any of this equation resolved and ejected with this will give you anything you want, depending on the question that you are given. So this is the equation of a progressive wave. And we're going to take a question on this whole setting, and you see how interesting solving questions on progressive wave equation is. Now, in considering the fact that we've seen equation of progressive wave, now we'll take a question from there. It said a progressive wave is given as this. The question will always look strange, but it is not. Very easy. It's one of the simplest calculations you can ever imagine as far as physics is concerned. So y is 0.5 sine 2 pi into bracket 40t minus 20x. You have something like this. Now, the first thing you are going to do is that the equation has been given to you. It's like a reference. You give you the equation. Now, after giving you the equation, you think, in the equation of progressive wave, which of them, I'll take the main one out, which of them can I manipulate together to obtain something that looks like this? It's easy. And what is that equation? Let's try this. Y is equals to a sine 2 pi ft minus 2 pi x over lambda. We have something like this. Very key and very important. You can get anything from here. Anything you want to get, you can get it from this extraction. So from here, the first question says you can get amplitude. Amplitude is equals to the value of A. And from here, if you compare this equation, A is equals to 0.5. And please, the amplitude is measured in what? It's measured in meters. Thank you. That's the first. And 2. That's the answer to the first question. Amplitude, A. That's A. Simple. So the second question is simple. If you look at this comparison, you observe that the first thing I'm going to do is that this equation here, I'm going to open the bracket so that I will have change it to 0.5 sine 2 pi times, that will give me 80 pi t minus times that will give me 40 pi x. That's the best thing you do. You open the bracket. So if you now look at this, you cannot compare them together. First of all, we are looking for something. We've gotten this. We're looking for speed. And how do we get that speed? It's easy. It's easy for us to get speed. We can get speed. So how do we obtain speed? For us to get speed, we need to look for, we have lambda, we have frequency. We need to find the frequency and also find the wavelength. Now let's find the frequency first, because you know very well from the back of your mind that V is equals to F lambda. So it's easy. Immediately you know the value of F. Yeah, you can calculate V directly from here, but it's better you do this. V is F lambda. After knowing the value of F, you know the value of lambda. It's easy for you to multiply and get the value of V. That's how a good student should think. Now, from here, I can obtain values like this. Already I have figure 1 directed. So from here, I look at this equation inside this place. Already, if I compare these two together, A is equals to 0.5. I've gotten as my answer. But if I look inside the bracket, it's easy. I can look at these two together and say, good. That is, what it means is that 2 pi ft is equals to 80 pi t. Beautiful. From here, I have an equivalence. Otherwise, I just cancel. You cancel that, okay. Pi will also cancel pi. What will be left here is 2f is equals to 80. You divide here by 2, you divide here by 2. The problem of f is 2. If you cut the problem off, what is left? So f becomes 80 over 2, which automatically becomes 40 hertz. So now, 40 hertz, we already know the value of the frequency. It's simple. So from here you've obtained the value of the phase. It's just equivalence. So from there you have f is equals to 8t divided by 2, and therefore the frequency is 40 hertz. Frequency is 40 hertz. So the problem we're going to have next is for us to now find the value of lambda, which is the wavelength. It's easy to find the wavelength. We have to find the wavelength. It's easy. And how do you do that? So the wavelength of this wave is something of this nature. Simple to find wavelength. So from here, if you look at this equation, so if you compare these two parts, you see that 2 pi x over lambda is the same thing as 40 pi x. So pi cancels pi, x cancels x. So if you cross multiply, you have 2 is equals to 40 lambda. So lambda becomes 40 divided by, 2 divided by lambda divided by 40, and that will give us 1 here, 1 here is 20. So lambda is 1 over 20 meters. Okay, that's the value of lambda. Now it's easy. Now we have lambda and we have this. So from there, how do you now find the speed? The speed is v is equals to f lambda. So that will be frequency is 40 and lambda is 1 over 20. So 0, 1, this. So v is equals to 2 meter per second. So that is the velocity of the wave. So v is equals to 2 meter per second. So class, it's easy for you to always remember that anytime you are given question that has to do with equation, progressive wave equation, just write out the equation according to the question, then look for the equation, or just write out this particular equation. Then from here, always remember that you can change whatever you want to change using v is equals to f lambda, or v is equals to lambda over t. So these two equations can change it to any form you want that will suit the equation that you're given. So from there, you extract, you're good. Now, that is that. So the last but not the least in the question said the period. How do you find the period? The period is simple. How do you get the period of the whole equation? The period is t. And how do I get that? What is frequency? My frequency is given as f is equals to 40 hertz. So my period will be 1 over f, which is 1 over 40 seconds. So period is measured in seconds. So now I know my frequency to be 40 hertz. So my period will be 1 over frequency, which is 1 over 40 seconds. So now you've been able to conclude this area of calculation. Please remember, equation of a progressive or traveling wave, all you need is get the Beza equation, extract any other equation you want to extract using v is f lambda, or v is lambda divided by t. Now that is that. So from there we want to move to the last stage of particle wave, and that last stage is simple. Let's talk about something called polarization. So after you call it, say polarization of wave. Now, first of all, it is one of the properties of a wave. But not just all wave. It is only transverse wave. It is only transverse wave that can be plane, that can be polarized. A wave that is being polarized is simple. The word polarization is obtained from a Latin word called polus. It's polus. It's the Latin word called polus. And the Latin word polus actually means direction or coordinate axis. Coordinator axis or direction. It actually means direction. Coordinator axis. That's what it means. So the word polus, which is Latin, and most inductive statements in sciences are extract from Latin. Good. Now, so polarization is simple. It's just a phenomenon. It's just a phenomenon. It's just an occurrence when light is made to travel in only one plane. That's just what polarization is. When you make light to travel in only one plane, one direction, it is said to be plane polarized. That's the word. Plane. Plane polarized. So when light is made to travel in only one direction, it is plane polarized. But one thing about polarization is there are substances that is our everyday that can be used for polarization, that can be used to make light move in only one direction. Anytime light rays that are scattered pass through those particular substance or materials, it just happens that the light will just be made to flow in only one direction or move in only one direction. Now, one of those things is the quartz. You have the quartz, you have things like tourmaline. They are crystals. They make, when light passes through them, scattered light, they collect this light and make the light flow in only one direction. Now, that is that. But polarization itself, as science grows, there become a need for building a standard thing that can, because of the need for polarized light, a plane polarized light. So there become a need for us to build something that can help us anytime we want to build a machine and we need polarized light in that machine. We just build something and fix it there that can help us plane polarize any lights that come in contact with. And there become a reason to build something they call polaroids. So polaroids basically are used for polarization. They are designed in such a way that they are used for polarization. They are a system of substances built to be used for plane polarization. It's just as if maybe think, okay, natural things, we also have natural things like calcites. They are examples of things, crystals, that can make light flow in only one direction. So if, for example, you have something like this, and you have a plane, maybe you have lights coming through this direction, and it passes, maybe you have another one where it passes through. Good. But by the time you have the same light again, and it's passing through, and this time you now have something like this, what you have done to this thing is, what you have done is that you observe that this light was passing through initially. What you have now is you have something of this nature. When the holes were standing at the same direction, you can see they are equal, they are standing in the same, as the light is coming, it passes through the pinhole down straight. But this time when it's coming, when the light ray is coming, it passes through this. But this time, this pinhole is no longer standing the way it was standing. It is now slant, inverted. So the direction has changed. So immediately it changes. This light that is here, that you discover that the light will not come out of here again. Here, the light will be caged in between here. So this cage line that is in between here has been plane polarized. So all you just need to do in your normal system of plane polarized light is passing through a system where there is hole, another system is standing, and they pass through. Normally that's normal light flowing. But this time immediately you change the direction of the ports where the light is passing through. The light you get in between, another light will not come out from here. The light you get in between become a plane polarized light. So polarization is very important in science. You observe that plane polarized light is used. The present day use of polarized light is that it's used for what they call HD. Your HD TVs, your HD equipment for production of HD, the high definitions, is the help of a plane polarized light. So polarized light is used for HD basically. Then HD, or you call it the high definition. Now, other things you can use it for is for sunglasses, because direct light is harmful to the eyes, but a polarized light is less harmful. It's better for the eyes than a direct light. So because of that, you see polaroids. Most time polaroids are created, they are used for you see polaroids are placed inside sunglasses. That's why when you see some glasses that people wear, see those glasses that they wear, you see them, you see there will be some structure inside, but if you don't look close, you will not notice it. They are majorly there. They are there majorly to prevent what they call direct light. So immediately the light gets here, the light will enter your eye, but it will become polarized before it gets into the eyeball for the iris to make use of. So basically, polarized light is very, very important, and you have so many other uses of polarized light. If you want to measure the level of sugar in your body, the doctors, the geneticians, the doctors, they make use of plane polarized light to test the level of sugar in body system. So these are importance and uses of polarization. But remember, polarization is just a way of making light to flow in one direction. And maybe it does that, it becomes plane polarized. And what are those physical things that you use in causing this thing to happen? That is, you have things like calcite, tourmaline, you have things like quartz. They are example of things that when this direct light passes through them, they become, the light that comes out in the opposite side become plane polarized. And an equipment that is designed to do this in what they call it, not in the natural way, but was designed as for technology, is called Polaroids. So when it's designed to bring about polarization, it's called Polaroids. Now, you can take that, but I think in 1808, I think a French scientist, I think it's Etienne Malus was his name. I think his name is Etienne Malus. Etienne Malus also was able to get a polarized light, but it was not a pure polarized light. But he tried in his own deduction. I will not forget to talk about his work. Now, Etienne Malus, his theorem was just 57 degrees, they call it. He said anytime light rays can be reflected because it's a wave. And one of the characteristics of wave is that wave can be reflected. So Etienne Malus talked about that if you incident a ray, this is the normal, that's N, the normal. If you incident a light ray, that the reflected ray can become polarized. He said it can be polarized. Only if it can be polarized, that's polarized. Only if this incident ray is at 57 degrees centigrade. Please take note of that, 57 degrees centigrade. Sorry, 7 degree. That's at 57 degree. Sorry, 57 degree. Sorry, 57 degree. Now, if it's incident at 57 degrees, that what you, maybe the light is incident at 57 degrees, what angle 57 degrees, what comes out in the other side become polarized. That was Etymanos. And it was later discovered that it was not pure polarized, but it was better than pure light. And those lights, it really helped in bringing about polarized light, which is present day important to our everyday existence. Thank you for coming to this class. We'll have a wonderful time. I'm your physics instructor. We'll meet in further classes.